So today we should go through finally the identification of dynamic systems. We were already doing some pretty dynamic stuff at the last lecture, where we were talking about the filtration of dynamic signals. I was there promising, yes, we will slowly transition from the static discussions to actually discussion about the filters, which in themselves are dynamic systems, because the filters transfer functions is the same thing, the two sides of the same coin. For example, in our low-pass filter, we wanted to have the gain of the filter to be 1 to correctly represent our long-term trends. We could choose the time constant in order to filter the noise that we considered to be noise. And we have also found out that this filtration can be achieved by something which we called finite impulse response model, or finite impulse response filter. The two sides of the same coin. We basically established this equation just by looking at the moving weighted average, and this type of model is one of the first models one can try in the identification of dynamic systems. So we will get back to this, and as promised last time, for example, if we needed this FEAR filter to represent the filter, we might be again interested in the gain. So low pass filter would typically have the gain of 1. High pass filter would be close to 0. Any questions to this? You saw this in your exercises. So today, first I would like to demystify what stands behind this finite impulse response. It may be good or it maybe extends how to think about the dynamic systems, the model of dynamic systems. And what's up, Jakub? Ježiš, okay. Painkillers. Okay, and so demystified, and then finally, okay, what we are used to, what is probably a task of identification that you have already done. A typical example. I have some time domain. At some point, I involve a step in my input. I measure the response of some plant, something like this, and then I'm trying to find out some sort of a model that would represent this plant. Let's say this is Y measured. And well, there are some textbook methods how to process these step responses. You have seen Straight's method, but the question is, do I every time get the data like this? So is it always that somebody will give me, here is the nice step response, we only jumped with one signal at a time, we measured everything correctly. It's not gonna be the case always, so the question is how to generalize this. So one type of this generalization. Let's maybe get to this. What do we mean by finite FIR? Finite impulse response. Where does this come from? This is impulse. Basically, we can get back in the past, or let's say back to the first thoughts about some dynamic systems. We traditionally represent some dynamic system as some input-output box, and what you are already used to is that it's not always good, or it's not good at all to live in this time domain. So it's much better if I represent all these signals in the Laplace domain. Why is it so? In the Laplace domain, we can calculate the output based on, of course, the input that influence the system, and based on some representation of the dynamics. And what we typically do, what we try our systems to resemble or to look like, is to have some linear dynamics that can be represented by the transfer function. What does this transfer function really do, and what would be its time representation? So if I'm in this picture, if I'm just staying in the time domain, well, I would use here some equivalent of the g of s, so g of t. And the question is, what is this g of t? Well, we can just try our Laplace transfer knowledge. So if our g of s would be, which one? Let's just do the simplest possible thing. How is this function gonna look like in the time domain? Exponential. What kind of? Minus one. There must be t.
T is in front of exponential as well, I believe. So 1/-1/t.
Yeah. So what was it? What I kind of remember is if I have s plus a, then it back transforms to e to the minus at, right? Okay. So if we use this, this is the Laplace.
It's the inverse.
Or let's make it even simpler. So that something like this.
However, now
So minus 1 slash.
Minus?
1.
Well, the A is 1 over T, right? T divided by T. Okay.
And also, shouldn't there be a time constant in front of the exponential? Because we changed the...
Yeah. I should have, but I'm just trying to make a simple example. So let's imagine this example was there at first. It, I mean, it wouldn't matter if there is this well, instead of 1, if there is 1 over T. So how does this g of t look like? If we are, let's say we go from 0 to some t, so at 0 we get what? E to the 0, so we get either 1 or some constant that is standing in front. Let's do some colors. Yeah, let's leave the colors for the later. And then what should happen as the time goes to infinity? Let's assume that the capital T is positive, so we will just drop to 0. Okay. And what does this represent? I guess you might have discussed this, or you didn't discuss it at all at your theory of automatic control. What does this G of S alone represent? What is this G of T?
Isn't it differential equation?
No. No, it's already a solution to a differential equation. So if our input is, how to write it well, if our input would be this unit step, we get a step response out of y of s. But if our, so this is step response. But what if our input would be this mysterious delta, which is nothing else than some idealized impulse, yeah, something like this, and well, if you look it up in the Laplace table, actually it's transpose 1 of s, or just 1. It's Laplace transform, or its Laplace image is 1. So basically, the response of the system to some impulse. So impulse means what? I just open a valve and then close it. Whether it's a valve which is feeding some liquid to a tank, whether it's a valve at this heating radiator, whatever like that. So basically, our G of S, G of T is nothing else than the response to the impulse, or impulse response. That's why there is the impulse response in the name of this finite impulse response model. So the word finite, we will get to that. just maybe think of this function for a second. Doesn't it really look like an impulse response? Yeah, just think of this kind of input. I have my tank fed by some liquid with a constant flow rate, and I just for a bit of the moment, I'm going from the steady state just by doing the impulse, like sudden twist, and then going back with some valve. Well, what would happen? Well, we are in the steady state, then the response to the impulse, if we are talking about the first order system, would be immediate, and then this whatever happened with the valve will slowly disappear over the time. Everybody somehow okay with this? All right, with this representation. So we might think, well, this is so nice and intuitive. If we give it a thought after some time, so why is it that we are using the Laplace transform? This is why we use a Laplace transform, because if we now take and we wanna calculate the response of the dynamic system in the time domain, well, from the notation side, nothing changes much. We just basically take into account what is the input to the dynamic system and what are the properties of the dynamic system. How would it react to the change in the input? But this innocently looking star actually is just representing some ugly thing which is called a convolution integral, or this is also called well, convolution product, whatever you might want it. And the integral, let's do it which way? There are two equivalent ways to write it, and I never remember which one is good for this lecture. U t minus tau d tau, and the other equivalent way is just flipping this t minus tau ut. Doesn't look as easy at the first glimpse. Let's just try to demystify it. What is an integral? Integral is trying to do like infinite sum over the infinitesimal portions of time. So let's say we have some input and output. I don't know, something like this. Now, let's say that we are at the particular time tk. This is the output of a dynamic system, and since the system is dynamic, it keeps the memory of what happened in the past. And well, what happened in the past is basically shown and in the graph of the input. And in the middle, well, this is the reaction of a system. How it reacts basically to each input that happened in the past. Let me somehow explain that. So, at the current point in time, the dynamic system would maybe barely react to the input at the current point, but it would react to how much valve to some tank was opened 1 second ago. Yeah, so it reacts to these past inputs. So basically, it would take into account the tk minus 1, tk minus 2, and so on. But if we go far enough in the past, we will quite likely encounter a point where, well, the input, how was the flow rate to the tank maybe 1 year ago, well, it wouldn't matter for now. Yeah, so that's why we take this function to our help, and this function now basically flips its axis. That's why we have this representation. So this function would just now start living in the past. So basically, it should say what? For the input that happened long time ago, let's say at point 0. That happened long time ago. So let's say at point 0, it would actually, is it correct order? Did I write it in correct order? Something tells me that the DSM just not interpreting it correctly. T minus tau. Something which happened a long time ago. Well, so what is this? We are plugging in tau. So long time ago, we are at the current point in time, t, this one. So the t goes in here and in here. And it now calculates what is the influence of the current input for the output. No, I got lost there. I have to start it somehow again. The whole point is the function g of t. G of t becomes like a weight. So let's maybe try to do it like this. So the function will take the value at different point in time and weight the corresponding outputs basically backwards. So it will weight the current inputs and those which happened in the recent past much higher than those inputs. So you have to imagine it like as we are traveling back in time, we are basically spreading to the left here and to the right here. that's what this minus should signify. So the input which happened long in the past would be weighted very less. Does this make sense? Yes or no? This is the question whether the weather on 23rd of April 2024 influenced the weather that we have today. Very little, yeah, 1 year ago. But the weather that we had yesterday, of course, influenced the weather that we have here, and the rest is just the mathematics. But this has tons of applications.
Shouldn't be the middle graph like inverse? Like if we start at time 0 and go to time t, the time is like the current time, is it?
No. So there would be, so current time would be, how would it be represented? Current time is here. We will take, so this is the, what is the current output? The current output is influenced, Jakub, how do you understand it? Yeah, it's basically, I mean, yeah, the graph is correct. Yeah, this is the reaction. So if at this point in time we have this input, the influence of this particular input at this particular point in time to the future would be like this. But at the next point in time, there will be a new input, which will have its own influence. That's why we are doing the integral. And now the whole problem comes when we are interpreting it, when we are trying to see it like what gave us our past data in the database, in the data that we wanna process. Yeah, so that's why the input back in the past would be weighted less. So that's why there is this minus. There should be tau here. That's why I was confused. Yeah. Okay. So if you buy this, has tons of applications. There are even convolutional neural networks. Let's just write this is convolution, has tons of applications in the image processing, but of course in the control, in the modeling. So now this will be a sort of idealized, even infinite impulse response model. So our finite impulse response model, so how did it look like? We said, we'll just wind back to our previous lecture. Oh, where are you? Ah, this guy here. So yk is equal to sum, and we were doing basically the same thing. We were traveling into the past with our control inputs. So yk sum of I going from 1 to m, biu k minus I. And well, we can start comparing these expressions. So maybe now this sort of, they are completely equivalent. This sort of formulation give us more sense, because here the input is traveling back to time. So it says again the same thing. It would be just an approximation. The input at the time tk, at time k, is given as a influence, collection, accumulation of what happened in the past. So here the integral is replaced. Already it's already only contains several terms. The coefficients bi are basically some samples, something like if we I need some different color. If we just sort of sample this function at the discrete point, so yeah, that would be our b1, b2, b3 coefficients, and we are just taking our past values of the inputs. Any questions to these comments? At least barely comprehensible. Good. Let's go now to the practical side of this. Let's get back to our question. Well, now we know our model can represent many different situations. How do we train this model? So let's just assume that we have conducted some experiment, and let's start from the step response, because we understand it, and let's try to see how we can use this model for how we can use the data for training this model. So what's our assumption? Let's say at certain time point, I think we can easily call it 0. We make a step response, and what would it mean? How would this look like in the output? Well, let's say something like this is the. Maybe I use. Yeah, something like this, that we don't have the need or don't have the assumption that the gain of our dynamic system would be 1. Good. So if we should train the model that would predict this, that would behave similarly to the data that we observed, then well, our predictions should kinda fit it. So this is of course 0 here. So what can we say or predict about the input? About the output at the time 0. So it's the time when the step just occurred, and maybe we haven't even measured what happened to the output. So we can just say, okay, this one, our output still at this point didn't notice that some change in the input happened. The fun will start now. So based on our model equation, let's try to see how would this prediction equation would be written. So if we take the sum, we need to have what? B1, and we would take what index of u? 0, right? Because so what happens here? Our k is 1, and we are just doing the first summand from the sum. So I is 1. This one is the easy one. What can we write for the B2? What kind of index will the u have?
-1.
Mm-hmm. Yeah. So one time back into the one step back to the past, which, well, according to our assumptions here, they are all zeros, right? So this is just 0 because we are just thinking about the step response. So the same would then happen, and our first prediction. So if we now take the BM, which one will that be? Which index of u? K minus m. Okay, but our k is 1, yeah, so 1 minus m, exactly. Very good. Yeah. Of course, we assume step response, so our input u was 0 in all these past moments. Yeah. Now we can even see why we wrote that this is 0 here, because, well, we are just assuming b1 times 0, b2 times 0 plus bm times 0. Okay, let's try to do another prediction of our model. How will this one go? So only k changed. Can be, but we can already be.
It's gonna be same, just u is gonna have 1 times larger index.
Makes sense, yeah. So B1, U1. Good question, Jakub, whether these are ones. We can just keep them general, and it will help us to generalize this. Is this correct? Yes. So, as Adam says, our B2 is now taking what?
U0.
U0 plus, and so on. What will this guy be?
2 minus 1.
2 minus m. Which sounds like we will be just now repeating this pattern. What does it mean? My output at the time point 2 is just given by the past, so past means the previous one, so 2 minus 1 at 1, 2 minus 2, 2 minus 3 until 2 minus whatever this number m is. And it would mean, okay, if we hit the time point m, how would this look like? Maybe. Or maybe not. No. How to get m minus 1, yeah. Yeah, it's back one step into the past. B2, this guy here. Yeah. You got it now. Now it's easy, right? And what about this guy here? U0, yeah. So while this one, well, that was still 0 based on our assumption of the input shape. Now we will actually have every term here will be some non-zero number. We can also so some time point m was some time point that we ran out of the coefficients of our model, but well, we can also predict in more into the future, or let's say we have more data. We have the whole step response. So how would even more general, let's say we have capital N number of the data points. How would that look like as a prediction? Un minus 1. Yeah. Yes. Yeah, it's like a crossroad. It's like Sudoku. Yeah, once you know the pattern, we get there. Why are we doing this? Well, if we just come back to our linear regression, well, we were trying to build some matrices, and then we plug in some of our data points in order to estimate the parameters. Well, how did we get there? Basically, we build up. Where was our matrix? Yeah, we built this sort of a matrices. Where is the expression I'm looking for? Oh, okay, this one. Yeah, basically build this form because our model was linear. Our prediction model was linear. So let's now think what is that we know, and what is that we want to estimate. Well, the left-hand side, the outputs, well, that's the step response that we measured, yeah, at discrete time points, and our U1, u0, u1, u2, whatever inputs are also data that we know, and our unknowns are of course these parameters, but they all enter linearly here. So what we can now do is the very same thing that we have done in the linear regression. We can just now build some matrix of this, or some matrix equation of this sort, where the vector p would contain all our data points. So let's try it. How would it look like? Doesn't really make sense to start with why not, unless we would like to estimate it, but that's already something advanced. Let's just put basically these equations into the matrix form. So we have y1, y2, what was our next step? ym and yn. We'll multiply this by b1, b2 until bm. Good. So let's do this practice. How to make it. How to build, let's say, the first row. So y1. What are the multipliers of the parameters? How will the first row look like? Once again. U0 and then 0. No, I didn't hear you. You can reply in Slovak, of course. I just didn't hear you. Good. What about what was it? There was U1. What about U2? Y2. So the coefficients of B1, B2 until Bm.
0, U1,
No.
U1, U0, U0, 0.
Ah. U1, U0, 0, 0, 0, 0. Okay. And well, we can start to see the pattern. U0 would kind of be on a diagonal. Let's see where the diagonal ends. So it's basically how to think about it, how to visualize it. I usually say, like, imagine we are just getting some sort of we just represent these u values as a sort of a strip, like on a piece of paper. 0, 0, 0, and here it's 1, which is actually u0, u0, u1, u2, and so on. And now we take this strip, we flip it, and we paste it at the correct place in this matrix. So if we just take this strip and we cut it, let's say here, that means we are actually representing the output at the point 1. Yeah, we take u0, 0, 0, 0, flip it. What is this? Vertically. So we get u0, 0, 0, 0. We get the second one. So now we have already a smaller strip. So we take u1, u0, or u0, 0, 0, 0. Good. How was our ym? Our ym, how would that row look like?
Y.
Yeah, we are in the past with that. Right, and then -2, and then dots. What will be the last one? Mm-hmm. 0. So this is actually where our diagonal would finish. This is actually the first time we are getting, like, if we are filling this matrix from top to down, this is the first time that we are actually getting a square matrix, right? Because now we have m rows, and we always had m columns. It's important because, well, at some point we want to do either let's say some inverse of this matrix, or at least pseudo inverse. Good. So this is kind of the first full row. Let's just finish the last one. So can we do it from the memory? Why? How would it look like? U n minus 1, n minus 2, n minus m. Yeah. Basically, what we got here, we can stop with our data points at this point. And basically, we would get a set of linear equations which are fully determined. Yeah, the square system. So we get m parameters that we calculate based on the m equations. It's okay, fine to do. Usually we just have more data. Usually we have noise in the data, so that's why we wanna take more data points. And of course, as a byproduct, what we got here, if we now just start this matrix from this row, we can actually represent. We can forget about the step response. We can forget about these zeros. Well, these sort of rows will always work for a general form of the signal. Yeah. Of course, the good assumption would be at least some steady state in the past, but it's not always necessary. So what are these numbers? These m and n. So m is nothing else. You would already. You would already call it this way at your theory of automatic control classes. That's the order of the model. And basically, this n is number of data points that we take into account. And this one should be, of course, we want to find m is the order of our model. We want to identify m parameters. So the number of data points should be at least m. It's very good if it's more or much more if the noise is high. Good? Does it make sense? All right. So let's now see how we can extend this, how we can maybe get to the types of models that you are more used to, because the types of the models that you are more used to would, in this discrete time domain world, well, they would look. First, let's get back and see. Last time we got our transfer function of the FIR model. Yeah, and that one is easy looking, very nice. It's basically just the numerator of the transfer function that you are more used to. There is one in the denominator. So something which is similar. Well, we can keep this I going from 1 to m in the numerator. BI U K minus no, what I'm talking about. This is transfer function already, yeah? This is not the time world. So this is z to the power of minus I. And we can extend this this denominator something like no. Oh, here it will be good to have one, because that's what you are used to see, and there is some z to the power of minus I. Right, this is a sort of a transfer functions that you have seen in your theory of automatic control. Too, there might be even some term which would be responsible. So this the number of the summands, these limits of the sums like n, m, and nk, it's what MATLAB uses. So I'm just using the similar notation. I don't know whether you, but you probably studied also this term in the theory of automatic control. What would it be responsible for? Doesn't ring a bell? When you are what happens, for example, when you are simulating, you have maybe an S function or whatever model that gives you the signal basically at the time t, and you wanna represent that since you supplied the input at time t, your next input is only you only get it at time t plus 1. What do you use in Simulink? What sort of a block? Mm-hmm. Yes. And what is the sign here, or what is the? Exactly. Which is just, well, this is just introducing unit delay. Yeah, so that current output is going to be the output at the next step in time. Yeah, we have something similar here. Yeah, this is again a delay, but a delay of nk number of steps. So this is the way how to represent time delay or input delay. And we will kind of exclude it from our discussion. It's maybe more important to look at these terms. So yes, this fraction here, this fractional transfer function, I hope it resembles what you see in the in the theory of automatic control, and what it would be called in the identification domain. This would be called autoregressive model with, I need to shift everything a bit down, with exogenous input. I didn't get this M there. Autoregressive model with exogenous genie, one more E, sounds horrible, I know. A, maybe make this R capital. Of course, the name is horrible, but we have a nice acronym, ARX. Let's maybe see how this model would again work in the time domain. So let's do the backward Z transformation. It should be easy. It's much easier than Laplace. What we are basically seeking to find is the expression similar to our Fear model. We should get something similar because, well, our numerator is the same thing as we had for the FIR model. So what do you say? How do we do that? We are slow or fast? You were pointing at the watch. Each Z to the power of -1 represents one delay. Z to the power of -2 would represent delay of two time steps. To the power of -3, 3 time steps. What do you say? How to start? Okay, let me.
Well, we can make like one large fraction from it.
Mm-hmm. One large fraction from it. Well, this is basically what we have. Let's just take maybe let's just take only this part to make it easy. The input delay can be always plugged in. Oh, okay. How did I copy this guy? Does it work? Yes, almost. One large fraction of it.
Or we can just multiply it. What we use.
Yes, yeah, so let's just do the, let's just get rid of the fractions by multiplying by the nominator, numerator, denominators. Denominators, so what we have, yz to the power of minus 1 times 1 plus sum of I until n, aiz to the power of minus I is equal to uz minus 1, and we have a sum I plus 1m b I z minus 1. And now what? I mean, we can basically keep these sums because, well, we have an alternative.
Isn't it already like just we just need to transform it now?
Yes, yes, exactly. Yeah, this one here is nothing else than no shift at all. So now we are just basically doing what? If we encounter k minus, sorry. So k minus I is nothing else than the z to the power of minus I, right? So the first term is what? Z to the power of 0, so yk minus 0, yk. Is it okay? You seem to be like shocked by this. Okay. Yeah, yk, current point in time, no shift, z to the 0, 0, 0 shift. Okay, and let's, since we can build then later our prediction equation, so let's keep this one on the left-hand side of our equation, and let's put the rest to the right-hand side. So we have here minus, and we can just live with the sum. This z transform is very, very nice that it's done so easily. And, well, no-brainer. We just have the z to the power of minus I. We just replace it by the yk minus I. Good. And what do we have here? We have here our u's. Same story with the u's. So we get sum from 1 to m b I u I k minus I. Yeah, this is our time domain model. How would this would be called mn or nm? Now I do not remember the order of these. Mn order ARX model. So why is this? Why this ARX? If you recall, how was this called? There is autoregressive, so that's AR part, and there is this exogenous input. Despite the fact it might be a little confusing, I give you that, despite the fact that here in the numerator we have what we before called FIR model. We are not calling this last part to be the FIR part, but this is this exogenous input. So this model could quite easily live without this. So in this form, this would be just called AR model, so autoregressive model. Why is it autoregressive? If you look here, it kind of resembles what we used for our filters last time. So the current, so the value of the output at current point in time is given by the past times, and this means that this model is regressing on itself. That's why the autoregressive. That's why AR came up. And if this model should also be influenced by some external factor, then it's not called external input, it's called exogenous input. Don't ask me why. There will be some historical lesson behind it. But this one can represent all the transfer functions, all the models that you are already used to quite easily. You might look, of course, at the poles, at the zeros. Everything is there. Let's see how we can do the same sort of exercise that we did for our previous FIR model, whether we can achieve it. So we can again assume the same setup, that we are just dealing with some step response data. We can just build our predictions. Ready for that? So how would our Y1 prediction look like?
Minus this one.
Yeah, but we need to now we need to break the sum into the individual components, because we want to get into this form. We would need to now see the structure in the multiplication. It's possible with the sums, but I think it will be more complicated. We wouldn't make our life easier. So what will be the first term? Mm-hmm. Mm-hmm. Exactly. Minus A1, Y, which one? Y0, Y0. Mm-hmm. Minus, and now in the same way as in our FIR model. Well, we assumed that before the step we were in the steady state. So our u's were 0, our y's were 0. So same exercise again. We are now having, let's just write it formally. So minus A2, what will be the y? Which one? Minus 1. Yeah. Until, okay, now it will be no plus, minuses, sorry. A-N. Now what will complicate our task is that we have M and N order. So the A's will run out, B's will run out faster than the A's. will the index of I of y look like?
Minus n.
1 minus n, right? Good, good. All right. Plus, we do not stop, we do not finish here, but we already know this one. Yes, this must be the same stuff as our very first FIR model. Yeah, B1, U1, U0, and then we are traveling back to the past. B1 U0 plus B2 U minus 1 plus BM U minus M? No, 1 minus M, right? Oh, the same thing. 0, 0, minus 1, and at the end coefficient we have 1 minus n. At the emp coefficient we have 1 minus m. Okay. Let's try y2. How would it look like?
Minus
Mm-mm. Adam is going to like it. I can see it. I can sense it. Minus a1, y1. Yeah. Yeah. So, yeah. Our coefficients are still the same. Yeah. The sum is still the same. So we will always have B1, B2, B3, A1, A2, A3, and so on. And what changes is the data. Yeah. This needs exercise, and you will get to that. So how was that? Minus A2.
I believe 0.
You will go with this one, okay. Until AN, and now Adam.
Okay, so a little bit more up. Or 2 minus n. Yeah, 2 minus n.
Good. Adam, your time has come.
Okay. Yes.
What yes? That was a subtle hint, but you didn't.
Okay, and it's
What is the K?
K is 2.
Yeah. What is I?
1. So 1. K is still 2. Now 0.
Perfect. Yeah. There is plus BM.
M minus. Two minus n.
2 minus M. Okay. Now let's do it similarly as we have done before. We got the pattern. Adam got the pattern. Very good. So now let's do some sort of a general term. Here it will start to get messy. which data points we ran out first, or in other words, what is greater, m or n? Which one is larger number? What you are used to, if you are dealing with the
Is larger.
n or m?
And
N is larger. Why is that?
because otherwise it would be physical realizovatelný system.
It's correct. Sorry, it's kind of correct. It holds more in the time domain. In the discrete domain, you can basically say it would be a waste of the coefficients, because you can more effectively, hopefully we will see it, you can more effectively store the past information in the states in the outputs. So you typically tend to have the n being greater or equal to m, which means if we are now going in the time order, so y1, y2, we will encounter more likely m on our way. So let's continue our nice game. What will the data that we will use for this prediction be like? Yeah, we can still make it there.
I is 1 and k is m, so m minus 1
Yeah.
minus 2.
Now it becomes tricky.
M minus n.
Ah. What about use? Did you spot the pattern that the use will always take the same indices? Yeah.
No, yes.
Don't make Jakub laugh anymore. His his teeth cannot stand it.
So m minus 1
Yeah. Ah, sorry. M minus 1 plus B2.
minus 2.
Mm-hmm.
Okay.
Kann sein. Good. Two more to go, and then we do the matrix, and then we say goodbye. So how will it be here? Perfect. M minus m, right? M minus m minus m, so 0. What about now? N minus 1.
Minus 2.
Mm-hmm.
And minus n, so 0.
Nice. Ah, no. Let's continue here. Mm-hmm. And -2 and the last one.
No, it's L minus N.
N minus M. Sounds good, yeah? I mean, the pattern is always N, we take the K, and we take this number when we subtract it, so N minus M. N minus M. Are you still holding for the... So let's say that we now take similarly to our FIR model, our capital N will be much larger than the number of coefficients that we have. What will be the most general, but I guess also most easy?
Isn't, wait, we have N and N?
We have capital N. Mm-hmm. Mm-hmm.
Why N minus 1? Isn't we just gonna be the same?
Almost.
N minus N.
Mm-hmm.
Is it all N minus 1?
Yeah. Exactly. Exactly. Nothing should change here. This is already following the pattern. N minus 2 plus
Again, N minus N.
capital. Okay. So, what about now putting this into the matrix form? Let's hope. I need to always make it in this way. So, what are our predictions telling us? So we have y1, y2, y. What was the first one? ym. Sorry, yn and y capital N. Our parameters here are depends. It's up to us how to order them. Let's say it's A1, A2, AN, B1, B2. Okay, that's already. Let's make it more condensed. Not sure. A1 until AN, B1 until BM. Well, this is the model that we wanna learn. We know Y's and U's. We need to get A's and B's. Right? We need to find out what are the zeros, what are the poles. Yep. So what do you say? How can we? How would this matrix look like? Let's start with the easiest one. So our A1. Let's plug in. Maybe we can plug in this these were the zeros, but we need to keep the columns in the place. Almost. Minus y naught, exactly. And then some zeros. And then I'm just trying to estimate the minus u naught. Is
Minus.
no plus, thanks. What comes next?
Those zeros are like the elements of the matrix.
Yes.
Okay.
Why is that? Well, how many columns we have? We have n plus m columns. Yeah, this matrix is white. What about here? Y2.
Minus y1. Then minus y0. Zeros. And I believe it's gonna be 1.
Yeah,
And
exactly. So how would the m look like without looking back?
minus
Y m minus 1, right?
m.
Until where did we finish these y's? So ym finished at. I don't know whether it's 0. This is already general. It can be. Yeah, but okay. You mean no. Okay. I know what you meant, but no.
Like before that.
Yeah.
There's gonna be.
M minus n.
But I just realized that it's gonna be somewhere moved.
This one? Yeah. Okay, the next row. This one is already easy, right? N minus 1, n minus 2 until y minus y naught. And in terms of u, we have, well, we are just repeating, right? No. N minus 1. How is it gonna be? Already lost track. N minus 1, n minus 2, and this is y naught, but m n minus m. And the last one, n minus 1 minus n minus 2 y n minus n u n minus 1 u n minus no. But the last one was capital N minus m. We have made it. You'll try to build these matrices automatically at your exercises. Did we get the same metrics as we should have based on the exercise? Let's hope, right?
Yeah.
Seems good. You will find out. Yeah, it's much better. It will be even much better exercise if we made some mistake, and you will correct that mistake at the exercises. Okay. Any questions, comments to that? You can say that you hate matrices. You're good, right? Okay. There are no comments.